Today we want to show the way from data to decision making, and there are different steps in between. First of all, we have to go from data to knowledge. What is knowledge which we can squeeze out from data? For that, we need data analysis, and there are several in use. I think several more are possible and would give relevant and further information without doing any more measurement. And our task, our way to get knowledge is to take the data, to put it in time sequences and to look on trends and so on. That means we get information about the rates of deterioration of track. How does it change over time in operation? And these rates of deterioration finally go into decision making, into all economic calculations. So that's the target for this day. I will start now with the first presentation from data to knowledge. After a discussion and breaks, Stefan Marschnig will speak about the innovative data analysis again, questions and answers and a break. And then he will go on with the rates of deterioration within the decision making. And finally, Petra Wiefling from First Alpine will show LCC track, their solution for calculating life cycle costs. We will then have a final discussion on the entire seminar of today and some previews for the next seminar. So when we go to development of maintenance, it's some things which we already mentioned in the seminars before. The maintenance is not penalized in the way that there is a scheme which is done everywhere and which is accepted everywhere. So it is in development. We started with repair of failure that was not very economic. Came up to time-based maintenance, which gave the same system, but on relatively high costs. Then people tell me that condition-based maintenance was the next step, though I'm absolutely sure that condition-based maintenance does not exist in reality. The next step is proactive maintenance, so it's predictive. That's the way where we should go. And it's not the last step. The last step is to combine maintenance with investment. So when we go from this so-called condition-based maintenance to the proactive maintenance, we need one thing which is relevant, and that's forecasting. We cannot base it on given status, we have to base it on future development. What we have to add in the next step is the life cycle management, and that means we need to take into concern investment as well to have a total cost of ownership model for decision making. That means to go to proactive maintenance, the big challenge is forecasting, precise forecasting, which is even more complicated as track is very different. We do it, or we show these ideas on the examples of track, or you can use it in whatsoever asset you want to use it. Would work for rolling stock as well. It works for all assets which are wear driven. When we go there, we need data. We do out of the data time sequences, out of this time sequences trend analysis, and with these trend analysis we can go for forecasting, for prognosis. This is a very simple way, a very simple idea. However, in detail there are some challenges to solve. Which questions do we want to answer with this way of thinking, with this doing? It's just 3 questions. asset management has just to answer 3 questions. That's very comfortable. The first question is, which track component should be used at which boundary conditions? That already means there are different components which would fit for different boundary conditions. That means we need a definition and an evaluation of an investment strategy. The second question is how to maintain these components as track itself. Again, definition and evaluation of the maintenance strategy. And the last question, how long to go on with this maintenance? What is the optimal point in time for reinvestment? That means we have to define the economic service life, and that's a pure economic calculation. So very simple, 3 questions only. Now it becomes a little bit more tricky because none of these questions can be answered separately. When we want to formulate an investment strategy, we have to know about the upcoming maintenance to make a proper decision. A maintenance strategy, on the other hand, must be done on the investment. It must be based on the investment. And the economic service life is a consequence of investment and maintenance. So it must be looked at more or less together. Furthermore, these questions require taking all service life into account because it's one of the preconditions for any economic calculation or evaluation, that you have to take all effects of a component or an investment into account. And the effects will be there as long as the component is in track. That means we have to go for service life. That means asset management must be based on life cycle management. Furthermore, this means the best, the most economic, and thus the most sustainable track does not exist. It cannot be one track which fits everywhere, or one type of component fitting everywhere. However, there are different best tracks, economic tracks, and sustainable tracks, but these tracks are different. So we have to define at which boundary conditions, which component, which maintenance strategy, which service life will be the economic solution. And this means it will be different solutions, sustainable solutions for the different specific boundary conditions. That further on means we have to go for detail into specific boundary conditions. What is a boundary condition? How do we deal with that? As I mentioned, asset management is life cycle management. We have to find 2 points together. It's technology, it's economy. We base it on data, experience, and understanding. Of course, we use tools, analyzing tools, simulation, big data, digital twins. But please keep in mind, these are tools and not solutions. Tools can help us. Decision thinking keeps on us. And we use these tools daily, but it is we have to be careful how to use. In future, this life cycle management, or actually this life cycle management is enlarged. Furthermore, the economic footprint is integrated into life cycle management. So we are speaking about sustainable, first of all, about technical and economic sustainability. And that means when we want to see a technical sustainability, we want to develop it, we need to think about quality behavior. Quality behavior is the technical description of a system. And we have to look if we can afford it, therefore we have to go for life cycle costing. Quality behavior is the technical understanding, life cycle costing is the economic understanding of assets. We have time sequences, we get deterioration functions, and so on. That's the technical side. We go for cost evaluations, that's the economic side. This together is life cycle management, and now actually we're integrating ecological aspects as the CO2 footprint and so on. This is quite good on the way already. You will later on see that these two things, the technical and economical life cycle management, integrated with the ecological one, works quite good together. We base it, as we are working mainly on track, we base it on track. We could also base it on turnouts or other components, but I think some of the solutions are best to show on track. But track, what is track? We're not speaking only about the superstructure, which is rains, fastening, sleepers, and ballast, because again, when it comes to economic regulation, we have to understand, we have to take all effects into account. And the deterioration rates is the target of our today's seminar. And the deterioration rate of the superstructure is not purely influenced by these four components, but to a big scale by the layer, by the dewatering system, and by the subsoil. Furthermore, of course, by the alignment, traffic volume, and rolling stock. So we have to understand it as a system. It's not a by chance mix of components. This is the picture why I do not believe in condition-based maintenance. You have an alert limit. You have any measurement which is better than the alert limit, so it is not a crisis. And now we have two solutions, and this is condition. This is your condition information. And with this condition information, you cannot do any decision. Should we go for maintenance or shouldn't we? Is it better to wait? We simply do not know, because we are not taking the time axis into account. We just have the distance between the measured value and the threshold value, and that doesn't tell us enough. If we look what is happening there, we will of course have different functions behind it. So different trends. If the sleeper is already broken, if we look at over time, the values will degrade quite fast, while on the right-hand picture, it is much smoother. That gives the information, that gives an idea where we have to look. If we want to have an information where we have to look, we go with a trend analysis further on, and we can calculate the point in time when we need to intervene. And you see on the left-hand side, that will be quite short. On the right-hand side, we have a lot of time. Therefore, and that's the step from this condition-based maintenance, just the two red dots, to predictive maintenance, where we take time sequences and trends and deteriorations into account. That's the way we have to go. Furthermore, you already know that from one other seminar, we have some experiences. We looked for functions. One of the experiences, a good track behaves well. You see it already here. This track is not good and it behaves badly. This track is acceptable and it has very nice behavior. You can write this in a very clear sentence: a good track behaves well, a poor one deteriorates faster. We change this sentence to this sentence: degradation depends on breadth and quality level. It's the same sentence, just other words. We just did that because if we take the second sentence and put it to a mathematician, he doesn't see a sentence but the equation, a differential equation, which we can solve. And that is the only formula which I present today as 2 times back also. That means the quality over time is depending on the initial quality of the investment or after a bigger maintenance job. And then it deteriorates more than linear, exponential. This is the quality behavior of track in general. You will tell me I just mentioned we have some different track. How can we have one iteration function? The differences are simply in two values in the initial quality in Q0, and by far more in the rate of iteration B. That is steered by a lot of boundary conditions, so we have to focus on that today. Furthermore, this formula puts together investment and maintenance, and it shows that we cannot separate it. They influence one another, and if we take further costs of operation hindrances into account, we have also the life cycle costs. That means we have the same formula which gives us the quality behavior and the cost structures, which is a very nice situation. Let's go one idea more with this function. I have a definition for investment and maintenance which would not make a bookkeeper happy. It is a pure technical definition telling investment just delivers quality, not service life. Of course, this quality is potential for a service life, but it is not service life itself. Service life comes from maintenance, which transforms this initial quality into service life. If you take a car, you cannot, and you buy a car, you do not have any information about service life, and you can destroy the service life of the car very easily, independently if this car is a cheap one or expensive one. In not putting oil into the engine, then these cars will die very, very early. So the maintenance, which transformed the initial quality of the car to service life, would not happen. This, unfortunately, is a real bad situation, or is a real situation. Quite often, very good maintenance investment is done, and then there's no money for maintenance. And that devaluates any good investment already done. If you don't maintain an investment and track which you invested for a lot of money, you will reduce the service level, not by some percentage, but down to the half. And then every economic efficiency is gone. How do we come to our data? We have a big treasure in our institute, thanks to our cooperation with the Austrian Federal Railways. We have the core network on the computer with all its data. All its data means we know which type of track is there, when was it laid, which components are installed. We have all recording car information. We know which maintenance is executed. And of course, we have transport data and the alignment of track. That means we look at recording car data a little bit different. Normally, it's looked over the positioning of track. So track location, and you see, you would look at like this. Oh, here I have a problem. Here it's quite nice. Here I have a problem. That would be the normal solution for that. We do it differently. We put ourselves on one point of the track and look how these track behave over time, and this allows us to do some trend analysis and to work out the rate of deterioration. That means at the beginning we have a maintenance or a reinvestment, then we have deterioration. We can put a trend curve into it. We have a threshold value. The next maintenance comes, the next deterioration follows, and we have these pictures. These pictures are in principle the same for every track. In the steepness of the deterioration, they vary very much, so it must be done specifically. The principle is simple. We have this e function, so exponential function, and I want, with a very simple idea, I want to show you how important this Q0 is. So the initial quality after investment or after a big maintenance job. What happens if we lower the initial quality? So the job was not done that proper. Perhaps the time slot for the work was short, so they had to speed up and could not work that precisely, or whatsoever. We reduce the initial quality by a little, by something. But that means S-track only knows I will behave due to my quality effect. And if I have this quality, I will behave like that. So this is the steepness here of the degradation. We can put this function to the left and we see a little reduction of quality gives much more maintenance demand. We have to go there. We reach the intervention level much earlier. That shows that obviously initial quality is quite decisive. Further on, we learned that then when we reach intervention level, threshold levels, we go for maintenance. We maintain track, and then it should go further on. But we learned it is not just this, because this would again be the idea. Here, track feels like here, and so it behaves like here. Just the function is going to the right. But we found a lot of sections where this exactly happened. We found a remarkable number of track which behaved worse than we expected, and we did not find many in between. So what was the question? What is, and then we analyzed the figures and we looked what it is, and we learned this point here, this red curve is practically what would happen here afterwards. That means track is repaired, but track does not feel repaired. It deteriorates as if it would not be repaired, of course from a higher quality level, but it deteriorates very fast. That was, again, some reasons to thinking. The reason was very simple. In the green picture, we do a proper maintenance. We eliminate the failure cause, the root cause of the failure, while in the red example, we do our own maintenance. We eliminate just the consequence of the failure, but the failure, the root cause of the failure keeps in there. And very practical example for that would be damping of a pumping section. When you damp a pumping section because the alignment is very poor, you can make track very plain. But the pumping section keeps in. And as you put more ballast there in damping it, the pumping section, the spring, ballast is a spring in our system, is higher. That means the pumping will go on and it will be faster than first time. And that's exactly what you see on the red line. There are some more understandings which we have to build up to thinking quality behavior. When we go on that, anyway, we come to the technical service life. We would not like to go until that point because you see here it's that much maintenance jobs to do. To say it in bad words, the machine which is coming from the maintenance shops meets the machine which is going to the maintenance shops. That's not bringing a lot of time, so not adding service life, but adding a lot of cost. So we would like to have not the technical service life, we would like to reach the economic service life. From that, we only know it must be shortened as the technical one. But intervention level, we could put a stricter intervention level into regulation. So put a stricter one. If we have a stricter intervention level, of course, we have to go for maintenance early. But the failure is not so pressed into the system that the repair action will bring us to a higher quality level. That means that deterioration is more flat. So the idea was we can put a little bit more maintenance and gain more service life. It turned out that this is not that simple, because if you go on here, you will see that the service life is even reduced if you keep this intervention level 2. Therefore, I have a very clear opinion about intervention levels. They are wrong because they are constant. They should not be constant. If you are strict at the beginning, then you later on can lower it to the original one, and then you really squeeze out service life. We get a lot of graphs of measuring systems. Here is an old quality figure. You can do it with standard deviation as well. We get graphs like that, as it's now guiding means. I'll come to that a little bit later. We are thinking here, we could think here we have a bad section, but this is for an evaluation length standard deviation of 500 meters. We go for 200 meters, we see the bad section is worse, but shorter. We go further on, we can zoom into the graph, and finally we see there is, on a 10 meter inferential length, we see it's not a bad section, it's a horrible single failure. And when we look at these peaks here, we also can identify that single failure because you see a lot of peaks here. And these peaks, the distances of these peaks are 120, 120, 30, and 20, and then we have some on 60. That's wells. So if we go into detail in our graphs, we see every well. These wells were quite nice. This one is a poor one. Further on, we have to think in the system. So we look one graph of the recording curve, we look the next graph, the next, and we see that where it was already poor, it became poorer quite fast. Where it was good, it kept good, what we mentioned in our formula. And here we could think we have 3 single failures, and that would be force us for a maintenance job, and this might be a good decision, it might be totally wrong, because we have to understand why we have these single failures. Might be there is a crossing, might be there's a turnout, might be there is a bridge. So we have to understand, analyze our system, our data in the system with all the information possible. Another solution, on another example, you see it deteriorates. Downwards is always poorer quality, and suddenly it's good. That means in between here there must have been a maintenance job. Track does a lot of things, but it does not become better by free will. What we learn here, and that's more important, I think, the failures which are coming later on, they are coming on the same points, in the same places. And we could make this, make use of it. Another example, on the left-hand side, you would say that's a very nice track, that's a very good track. And on the right-hand side, that's a poor track. Yes, normally it will be like that, but it also can be a very new track and a very old track. And it might be that the right picture is quite acceptable for the old track. The left picture always looks nice, so this is good for new track, of course, as well. So that means look at the data, the recording card data, but add the information before going to conclusions, to decisions. We learned one very strict relation, which is very, very helpful for progressing. We learned that especially the damping cycle and the service life are strongly interacting. That means if we have a longer damping cycle, we can't accept a longer damping cycle because of quality reasons, because we do not work, we do not do maintenance. So if we can do a longer damping cycle due to quality reasons, we will get a longer service life. This is quite helpful for prognosing. And here we put in all different types of track, curves, straight sections, different superstructure. It always showed this same picture. one of the seldom cases that the picture doesn't change with the components. However, drag in fact behaves like this. It has a part of this exponential behavior, but it has two sections of logarithmic behavior, which is exactly the opposite. The first part is very simple. That's the initial settlements, every building, and drag also, of course, settles at the beginning a little bit stronger. This stops, and then the exponential behavior starts. However, in drag, we learned in some seldom cases, we saw that the logarithmic behavior came back. And this happens when the ballast is already that polluted that you do not have free space in between the ballast stones, so you cannot settle anymore, and then it becomes very stiff. That means it's a poor quality, it's very stiff. It has then more or less, if you look here, it has more or less no deterioration. Would be the best situation for maintenance guys, because no deterioration means no work for them. However, this is the most dangerous situation at all, because this, as the system is totally stiff, it's overloaded, and it can break or collapse at any point in time. However, this part of the function normally doesn't occur, because normally the quality it's in this range is that poor that we cannot accept it and change, have a threshold which is high. So this area is not in our interest. The threshold value will be anywhere here. I hope you can see my cursor. So let's come to it's now I have tried to bring some ideas about thinking qualities. Now let's go to data. What we are doing very perfectly is we are monitoring. Then we get data. Monitoring we can do in different ways. The vehicle measures the infrastructure, that's the classical recording car. It might also be from a train. The infrastructure measures the vehicle, that's fixed points of the infrastructure, looking if the wheels are around and things like that. Infrastructure measures infrastructure, is also a possibility with a lot of sensors, or vehicle measures vehicle, so that the reaction of the vehicle during the run is checked. That means a lot of data, and the data sources grow. Again, we have data. Now I see a big problem. We have to organize that. We organize the data in 5-meter sections, and we put all the information we have in these cross sections. That means data about superstructure, asset data, machine operations. That's status data. But we want to put in track behavior data, deterioration rates. We want to put in everything which is below the superstructure. So the technical track review, water situation, ballast, substructure, and sub-ballast should be. And of course, from the recording car, we take more signals. There are a lot of signals which you can use. And even if you use some signals together, you can get a lot of additional information. This is just organization of the data. What I often saw, this data are put in warehouses. It's nice there. And then I took the internet, and this was the picture for a warehouse. This is not changed. You have a big entrance. What I am missing very much in this picture is the exit. And I see this, unfortunately, in some practical situation that the data are stored, full stop. But that's not relevant anymore, because now we put the data into clouds, but it doesn't change anything of the problem. When we put it into the clouds, knowledge doesn't come out of the clouds as long as we don't use analyzing tools. I think there are so many data which we put anywhere and never again looked at. These data are for nothing, should be analyzed, then it would help. So we come to the core part we want to go from data to understanding, so we want to go from data to knowledge. Unfortunately, this is not a direct way. And this is not a way which you can through program. No recording card can deliver knowledge and action plans. That's simply not possible. Because first of all, when you have data, you need to verify them and to look if they are complete. Verification is quite important because as soon as the data are put into a warehouse or a cloud or a server, then you cannot anymore verify them. That must be before. When we have verified them, then we have to synchronize the data. Synchronization means you have a recording card which has a lot of data, different measuring systems, and these different measuring systems do start differently, so they are not in phase. You have to synchronize in one recording card run all the data measured. That's quite simple. More tricky is the positioning, because you have the recording card tells you these are the data, and here this point is kilometer 100.0. Next recording card run, it will again tell you this kilometer is 100.0, but these two 100.0 are not the same point. This depends on the situation of positioning. It depends on the slip and whatsoever, and you have to correct it. In Austria now we have DGPS and corrected by fixed points on the electrification mast. So for track, this positioning is fine. It does not meet the demands for turnout. We have to do more for the turnouts. When you have got these data into a positioned way, and only after that, you can do time sequences, because then you are sure to take just the same point in a time sequence. So you see really the change of behavior, the behavior of this point. And when you look on a turnout, you need this on a track. This needs a preciseness of, let's say, 1.5, 2 meters. That does not change so fast. If you go for a turnout, it must be much more exactly, because if you have a data from a turnout, and this data is by chance a little bit ahead of the frog, and next time a little bit after the frog, these 2 points have nothing to do with one another, and you need to have a very precise positioning that we are able to go for time sequences. As soon as we have time sequences, now it's really simple. We go for trend analysis, and we learn the track does a lot of things, but track does not change its behavior as long as we do not change the boundary conditions. So if we put on much more traffic, it will change. If we keep the things in the same situation, it will keep as it was. That allows to go from trend analysis to prognosis. That allows to go from the so-called condition-based maintenance to a predictive maintenance. And that's the way to get understanding of the behavior. And that's, in my opinion, knowledge. So these data here are the raw signals from the recording card and the turnout. These signals are not positioned. With these signals, they cannot do every color as one recording card, so we cannot do any time sequence. We developed in the institute an algorithm which could make out of the upper picture the lower picture. Here you can make time sequences in cutting it and telling, okay, I take the point 1000 and look how it changed here. This works. So repositioning of that is a precondition for trend analysis. That means please store the raw signals and store the repositioned signals. Maintenance action will change the trend. So a trend is always from one big maintenance action to the other. And what's quite important, just data of loaded measurements allowed random analysis and thus predictions. If you measure something in a turnaround track unloaded, this will not give you information of the behavior. It tells you the turnout is there and the turnout has these differences, but it doesn't tell you how turnouts react on track. So we need loaded measurements. And of course, our formula has just two parameters, Q0 and the B rate. If you have just two measurements, in theory, that would be a precise prognosis. In practice, of course, you have some failures and so on. It will not work. The more points, at the beginning with 2 points, measuring points, the distribution function will be quite flat, so the prognosis is not that precisely. The more points you can add, it is the stricter and the clearer it is. We normally start with prognosis from 4 measuring points onwards. We have to understand what the recording car is measuring and what we are doing with this recording car. Normally now we have gliding means, so gliding values for the standard deviation. That means if we have an evaluation length, half of the evaluation length ahead, our point which we are measuring, and half of the evaluation afterwards is influenced. And then we go 1 measuring point further on, and also the 25 centimeter, and that gives us a signal which is showing a graph and not steps. And of course, we can change in evaluation of the raw data, therefore we need to store the raw data as well. We can change this evaluation line. That means if you have a point of disruption on that point here, and this would be the recorded signal, it's nice, we can work with this. But if you want to go for a standard deviation, it has always the influential length. And you see there's no influence here with the point of disruption here, not as well. But here already we have some influence, and we have it until we are away from that point. That means the standard deviation signal would look like that, and the point of disruption has an influence half of evaluation length before until half of evaluation length afterwards. In analyzing, you should take this into account. The old way was to have fixed measuring length and then to build the average quality figure. And this average quality figure is for the next section. It is different. That's so far so nice. However, these jumps, these points are not existing because that's just by chance. If you would take another starting point and the jump would be on another place, it has nothing to do with rank quality. If you go with guiding means, then you have good functions. We need to think on data quality, which is a precondition. If we have poor data, the prognosis will be poor. We have to think on outliers, what to do with outliers. We have to put into the maintenance. You see it became poorer here, and then suddenly it became better. So most likely here was in the maintenance job. We have to take all this to account to know where we can go with an iteration function. Nevertheless, we sometimes see astonishingly pictures. And of course, first of all, if the picture doesn't fit to our ideas, track is right. And we have to think on our ideas. So we have to go there and look. You see, this track is perfect, very little deterioration. But the blue bar means anybody here went for ballast cleaning. The track was perfect. They did some ballast cleaning, and now the track is poor. So this is a strange situation, and we have to clear it because perhaps something in our model is not proper. Fortunately, it was not the model. Fortunately, it was missing data. And the missing data was before the blue line, between that measuring point and the ballast cleaning, there was a landslide. And the whole track disappeared below that landslide. Of course, they had to clean the ballast, but they did not clean the ditches good enough. Therefore, the deterioration is still poor. So it was a question of data. We have to look on that. Now, which regression function is the right one? I told you we have an E function, an exponential function. We have here some data. We can do it linearly. We can do it whatsoever. If we do always 1 degree of 1 potential more than the number of points, it fits quite nice. But why should a track behave that strange? That is absolutely just a mathematical as if good prediction. It has nothing to do with track. What we are normally doing, in spite of our idea that we have an exponential function, we take a linear model between two maintenance sections. Because between two maintenance sections, there won't be a big difference between an exponential model and a linear model. But after every maintenance section, the steepness of our degradation changes. So we always put in the tangents to the E function. To picture also the overall nonlinear behavior, but in detail we go for linear behavior. We learned something more. Here we put on 2 tracks on 1 picture. This is a quite nice track, but steep degradation. This means that they went for subsoil rehab. And this track is afterwards that track here. Another track, even worse, same subsoil rehab, came to the same values, but it deteriorated faster. And this is by a lot of practical track workers. This is called the memory of track. In fact, it just shows out that this steepness has the reason which is steeper than what you can realize with ballast cleaning. Therefore, you can bring it down, but it will still have a slight steeper degradation. So it is good to do this ballast clean, this subsoil rehab, but it won't bring a very, very poor and a poor track to the same behavior. And another idea, we always look to the values of the recording cutout. We always look to the values, the amplitudes, but we do not look to the wavelength. And this could help. Stefan will show you in detail about that. Tools are helpful, but superstructure influence track deterioration. We took big data. We put in all track. So to say, the blue is a light track with concrete, with wooden sleeper, and a light track with concrete sleepers, a middle track, and a heavy track with concrete sleepers. We put that all into the big data system and ask the system to tell us which track is the best, which track has the lowest and the highest degradation. And we learned that the best track, the heavy track, has the highest degradation. This is not feasible for the first point. There's no mathematical mistake in it, but it's not logical. Why? Of course, because it was a general analysis. And big data cannot give us answers with general parameters. They must be parameter specific. What we learn here is that the railways know exactly where to put the best track, because that's where we have the biggest, the highest traffic volume or sharp curves and so on. And of course, as they are loaded much more than these tracks, the deterioration is high. So the tools help, but we need to think. And the only way to use these tools properly is that we do it on a parameter-specific basis. Then we can get out a lot of answers. However, actually, we run into a bad situation which will become worse. The target of the European traffic policy is shift road to rail. And in Austria, they have made a lot of success in that. And the target is to double rail capacity by 2040. Why this is a problem? This is a wonderful situation that this is, we can realize things like that. However, we run into a problem between availability and maintenance. We double rail capacity. We will have more trains, we will have heavier trains. This means we will have more deterioration. This means we will have to do more maintenance. But when we have more trains, we won't get the time for more maintenance. And this will be the coming problem in the railway system. It's not just Austria. How to solve that problem? Again, it's sustainability. We need to construct track which requires less maintenance. Just to do less maintenance would be absolutely the wrong way. But to construct a track which requires less maintenance, this could be a way out of that. So it will be a race between demand from more traffic and ideas for more sustainable systems. And this goes for trend analysis, and with trend analysis, you also can make demand prognosis. Here we calculated for a part of the Austrian network. It's not the entire network. For the entire network, the figure would be at the beginning roughly 200 kilometers. This is a part of the Austrian railway, and we calculated when there will be how much renewal demand will be. So the blue is the first renewal set, then the yellow, and so on. And you see, this is the prognosis for renewal demand. In 2016, already there was an implementation ongoing. It started actually in 2009, which reduced this demand dramatically. So we had a success in constructing track which is more sustainable. And if it's more sustainable, it keeps longer, more service life. That means it reduces the renewal demand. Of course, that goes time by time, because if you think we have, let's say, 5,000 relevant kilometers of track, and we do 200 kilometers of renewal a year, it takes a time until this system is in the entire network. But it reduces the demand, and that's what we need. But that's only the half of the answer. Because now we come to this situation, which I described before, and this situation meant we get more traffic. More traffic, more maintenance, less service life. That means that reacts in the other direction. And when we just put in 2.5% of increase of traffic, it would be like that. So after a certain period, the benefits from this higher sustainable track, from the better track, is more or less eaten away by more traffic. This does not mean that we should not go for more sustainable solutions. This means much more. This means innovation into sustainability is a permanent demand, and we must do that always. We must have, after this first innovation or this innovation, reducing our demands, we need this next innovation, the next increase of sustainability, so to keep it down. And that's the race, which I meant, the race between demand and innovation. That will be a permanent job, and the more success we have on the market, the more we have to do in that, and we have to identify how to do it. And our ideas, I wanted to show these basic ideas before Stefan goes into details, is that we go for understanding of track, for deterioration. That means the logical way for innovation, in my point of view, is to analyze all the data, to look on in which situation we have bad degradation function of a component. Might be that component is very nice, some boundary conditions, but not fitting to another boundary condition. Having a high deterioration rate, we know we have to do innovation for that component under that boundary conditions, and then we can go forward. That's the ideas behind steering the whole life cycle management by deterioration rate.